Okay, so what I'll talk about is representing numbers, and in this number system we're very accustomed to is the decimal system. So if we wanted to represent a number like this, 1,543, we're using 10 different symbols, the symbols 0 through 9. So a set of 10 different symbols. We order them from lowest to highest. And then once we use up one of the symbols, if we want to do the next highest number, so for example, the number after 9 would be, we're now out of symbols. We went 0 through 9, so we don't have an 11th symbol to use. So what we do is we send this one back to its original number of 0, and then add 1 to the column next to us, right? And just do that, and assuming you have infinite space, we could keep doing that. So that's the next number after 9. So we only had 10 symbols, but this is really starting at 0. This is the 11th number. We only have 10 symbols, so that's the system we use. So that gets the idea of a base, and our base is going to be, in the decimal system, the base is 10. So you could think of this number as being 1 times 10 raised to the third power plus 5 times 10 raised to the second power plus 4 times 10 raised to the first power plus 3 times 10 raised to the 0 power. Right? So that's really what we're doing. We're saying each one of these columns represents a number, but we're multiplying that by 1,000, multiplying the 5 by 100, multiplying the 4 by 10, and multiplying the 3 by 1. So this is something, obviously, we're used to. If you wanted to represent numbers in binary, so for example, if you wanted to represent the number, we're going to use this notation. We'll put a 0 and a little b to mean binary. So binary means that instead of having 10 symbols to represent the numbers, we have 2 symbols to represent the numbers. So the 2 symbols are a 0 and a 1. So for example, if you wanted to represent the number 0, it would be like that. If you wanted to represent the number 1, we go to the next symbol, which is a 1. Now if we want to represent the number 2 in binary, already we're out of symbols. So this would go back to the beginning one, which is 0. And then we add 1 to the next column. So that's 2. Now if we want to go to the next number, we just add 1 to the lowest column, which is that. That's 3. The next number after this, we would add 1 to this, but we're out of symbols again. So we would make this a 0, and then we'd have a carry into the next one. And a 1 plus a 1 is 2, which is 0, with another carry. Right? And this pattern goes on. So we'll use this symbol of a 0 and a little b to mean what comes after this are just using the binary symbols, which are just 0s and 1s. So for example, if we wanted to have the numbers 1, 0, 0, 1, 1, 1, what does this equal? What this really equals is, this is to the 0 power, 1, 2, 3, 4, 5. This would be 1 times 2 to the 5th plus 0 times 2 to the 4th plus 0 times 2 to the 3rd plus 1 times 2 squared plus 1 times 2 to the 1st plus 1 times 2 to the 0, which ends up equaling 2 to the 5 is 2, 4, 8, 16, 32. 32 plus 0 plus 0 plus 1 times 4 plus 2 plus 1. And this is 32. So this equals 39 in decimal. So this represents the number 39 in decimal. And then if we wanted to use another numbering system, So really, so now we kind of get the idea. We're used to decimal. We've been using that our whole life. But really, we could use any numbering system. You just need to know how many symbols are there. And you just keep adding a symbol until you get to the last symbol. Then you go back to the first symbol and add one more to the next column. So for example, hexadecimal representation uses 16 symbols. And the 16 symbols are, and a whole lot of thought went into this, 0 through 9. And then for the 10th, 11th, 12th, we'll use A through F. So that way we have 16 symbols instead of 10. So we could represent the number 6 in decimal. Let's do this. Why don't we have a chart? We could say decimal, binary, and hexadecimal. So what we could do then is we could say, for example, if we wanted to represent numbers like, let's say, 6 and 14, what would we do? So in binary, it would end up being, we'll put a 0 with a little b here, and a 6 would be, I'll use 8 bits. And the reason I'm using 8 bits, it'll become clear when we do hexadecimal. But what would 6 be? 6 would be a 1 and a 1 with a 0 after. And intuitively, a 6 in hexadecimal, we'll do a 0 and we'll put an X here, meaning hexadecimal representation. What would a 6 be in hexadecimal? Well, we said we're using the symbols 0 through 9 as our first 10 symbols. And then the way we represent an 11 is an A, and a 12 would be a B, and so on until you hit 16. So a 6 is pretty easy. And maybe I'll use 2 places, but it would be the symbol 6. Okay. For 14, the binary representation would be, so it would end up being 8 plus 4 is 12 plus 2. That's it. So it should be 1, 1, 1. Should be like that. And the hexadecimal version of it, so this is the thing that takes a little adjusting to, is after 9 comes the symbol for 10, which is A, and then 11, B, C, 12, 13, 14, it would be E. So it would be, let's say if we did it with 2 places, it would be 0, E. Now, the connection between binary and hexadecimal is if you group all your symbols in sets of 4, it takes 4 binary bits to represent 16 different things. So each one of these turns into a hexadecimal symbol. This 0, 0, 0, 0 becomes 0, and 1, 1, 1, 0 is 14, which is E. So really, any dump of data of zeros and ones, if you just group them into sets of 4, you can rewrite it in hexadecimal. Okay. So now, since computers run on electricity, let's focus on, and electricity is either on or off. We like representing data in binary values of either electricity is on or electricity is off. So, if we wanted to add 2 numbers together, like 6 and 14, use the same numbers in our example, and 14 would be 0, 0, 0, 0. We said it was E. If we wanted to add these 2 numbers together, how does adding work? So same concept as decimal. if we had the numbers 4 and 16, what would we do? We would take this number, the smallest significant column, add these two together. If their total can be covered by our symbols, then we'll use it. But we can't, because 10, in decimal, 10 plus 4, I'm sorry, 6 plus 4 is 10, and we don't have a symbol for 10. So the way we represent a 10 is with a 0, and then send a carry to the next column. So we put a 0 here and then push a 1 to the next column, meaning 1 times 10 raised to the 1 power would get added to whatever the total comes here. So if we don't have a symbol to represent the total, because it's bigger than our biggest symbol, then we push a carry into the next column. And so then the 1 plus 1 would be 2. So in the decimal world, 6 plus 14 is 20. In the binary world, it's the same concept. Add these two numbers together. If we have a symbol that can represent it, great, we're done. If not, then we push the symbol to the next column and use whatever the remaining value is. So 0 plus 0 is 0. 1 plus 1 is 2. We don't have a symbol for 2. So we put a 0 and we have a carry. 1 plus 1 plus 1 is 3. We don't have a symbol for 3, but we can represent 3 with a 1 and a 1. So we'll put a 1 here and do a carry of 1. Then 1 plus 0 plus 1 is 2. We don't have a symbol for 2, but we could put a 0 and have a carry. 1 plus 0 plus 0 is 1. That one we have a symbol for. So we put a 1 there. And then 0 plus 0 for the rest of the way goes like this. So that's the binary version of it. The hexadecimal version of adding is, what did we say? It was 6 and E. 6 plus 14. Do we have a symbol for that? Well, we went 6 symbols past E. We only go up to F, and then after F we don't have any more symbols. So how many things after F did we go? We went, let's see, 1 would be F, and then 2, 3, 4, 5, 6. 5 after? Well, if we went 1 after, that would be a 0. So then we would use the symbol 4, and then we'd have a carry of 1. And then the carry of 1 would be a 1. And we could double check that by grouping our binary versions into sets of 4, and they should match exactly. This is a 4. 0, 1, 0, 0 is a 4. And 0, 0, 0, 1 is a 1. So this is the hexadecimal representation for 20. And if you think about it, it's whatever number is in here, this gets multiplied by the base of not 10 as in decimal, but by 16. So this is really 16 plus 4 is 20. 16 plus 4 is 20. And in the decimal case, add this together, you get 20. So the mechanism for adding numbers, it's the same exact thing, just taking this column and then possibly a carry in. And so we'll, later on in the course, we'll learn how to make electronic equipment that does that. It would actually have to have 3 inputs. The 2 inputs plus a third one for the carry bit. It would have 3 inputs that are either electronically on or off, and it would have 2 outputs, the total plus the carry into the next column. And we could wire those together and then be able to take 2 binary numbers and actually add them. So we could perform a piece of mathematics doing that. Okay. Now, if we wanted to do subtraction, how could we do subtraction? Subtracting 2 numbers. So is that any idea if we wanted to do, let's say for example, we want to do subtraction. As the course goes on, we'll come up with better solutions, but just to try to convince ourselves we might be able to do subtraction. Suppose in the decimal world you want to do 14 minus 6. What do? Well, you say, are there enough units here that I could subtract this many? And if there are, just subtract them. Well, let me do an easy one. 18 minus 6. We can subtract 6 from 8 and get 2. Nothing to worry about. We subtract 1 minus 0 is 1, and we're done. So the only case we have to worry about is when what's up here isn't enough for what we're subtracting here. So let's do it at 14 minus 6. In the decimal world, what we do, let's say minus 0.6. The decimal world, what we do is we borrow from the next column. So we subtract everything that's out here, whatever this comes to, because this is all one power higher than this column. We subtract 1 from what's in this maroon box and move it over here. So this would then become a 0. And then we can now we consider this whole thing as a decimal symbol for 14. And we can do 14 minus 6 is 8. And now that we've subtracted 1 from here, we've kept the bookkeeping the same. We've made the value of the top number the same. And so we would get 8. If we wanted to do the same thing in binary, if we wanted to say 14, which is 1, 1, 1, 0, minus 6. I want to make it interesting. Let's say minus 5. If we wanted to do 14 minus 5, how can we do this? Well, what we can do is we can say, I'm going to borrow 1 from what's out here. So I can make this a 0 and borrow 1 here. And then do this plus what we borrowed, subtracting this one. We could get a 1 here. And now the zeros worked out okay, this worked out okay. We ended up, this one wasn't too hard. We ended up with 8 plus 1 is 9. But if we wanted to electronically wire something together that it could always do this, what would we have to do? We'd have to somehow keep track of what we're borrowing from the next column. And you know, sometimes you borrow from the next column, which means, and it doesn't have anything there, you have to borrow from the next one, and so on. It could go a long time. So there could be some bookkeeping involved. But we might need a series of memory things that tell us how much we borrowed from the next column. But it would be doable. And suppose we wanted to, we'll discuss in a little while a better way to do subtraction. But what about multiplication? Is there a way to multiply 2 numbers together? So suppose we're multiplying in decimal, 14 times 11. What are we actually doing? Well, we're saying this number times this number is 14. And then for the next one, we kind of slide it over 1 power. And then we multiply, well, let me make it a little more interesting. 21 times 14. We put a 0 here, which really means whatever result we get from multiplying this times this whole number, we just slide it over 1 power. So in the decimal case, we're multiplying this result by 10 by putting a 0 here. In the binary, we'll put a 0 there and still slide it over. Same concept. So 2 times 14 is 28. And then we add this together. 4, 5. Hopefully that's right. If you want to multiply binary numbers, what would the mechanical operation be? Suppose you wanted to multiply 14. 8 plus 4, right, 14 times, no, 5, let's say. How would we do that? Well, it's kind of the same way we do decimal on a blackboard. We could go like this. We could say 1 times this whole number. Then slide it over 1, multiplied by 0, so we don't even have to do it. Slide it over a second time. Well, I mean, you know what I mean. Let me just write it out. Plus that, plus 1 times this number again. 1, 1, 0, plus 0, 0, 0, 0. Add this all up. Right? That would end up working. So we just add this up, 0, 1, 1. This is 2, so that means 0 carry the 1. 2, that means 0 carry the 1. 2. That's right. Oh, that's right. So what am I doing in decimal? 14 times 5 is what? 70. And what do we have here? 1, 2, 4, 8, 16, 32, 64. This means 64 plus 2, 16, 84 plus 2, 70. Okay, good work. Okay. So really what we could do, so what we're trying to do is we're trying to convince ourselves that we can do mathematics if we had electronic equipment that could do the steps we're trying to do here. What we really have to do is take this number. We could probably build a piece of electronic equipment that could very easily multiply it by 2. Just put a 0 next to it. Take any number. If you want to multiply a number by 10 in decimal, just put a 0 on the rightmost column. If you want to multiply a number by 2 in binary, just put a 0 next to it. So what we could do is we could actually do a series of adds to replicate multiplication. We could take a value, set it to 0, then add this number to it, if that's a 1. Then double this number by putting a 0 in front of it, and if this is a 1, add it, if not, skip it. And do that. So it would take 4 adds. For each bit of the second number, we'd have to do another addition. And we'd have to do this concept of shifting the bits over by 1. So we'd have to compute 1, 2, 3, 4 numbers and then add them all together. So for every bit here, for every bit on the second number, there's 2 steps. But it's doable. Obviously it takes longer to multiply than add. But it's a doable operation. Okay, so the reason we're representing numbers in binary is because computers run on electricity. So we need to design electronic components that will take a bunch of wires that either have electricity on them or not, wire them together, and then do things like add 2 numbers together, multiply 2 numbers, perform mathematical operations. So far we've talked about representing numbers, but the numbers we're representing are positive only, right? So we're basically saying like 0, B, meaning binary. 1, 2, 3, 4. That's 14. That's positive 14. But all the numbers are positive, right? It's like we're starting at 0. If they were all zeros, that would be 0. And then as we add bits, they just get more and more positive. We might need to represent negative numbers. Suppose we wanted to represent positive and negative numbers. How can we do that? So, any suggestion? Well, so we only have bits. That's the only thing we can use. One way we could represent negative numbers is to pick a bit, and we'll say if that bit is one value, it's positive, and the other value, it's negative, right? Could do that. So one of the early representations for negative numbers earliest representation for negative numbers was to take the bit we're least likely to use, the highest order bit, and say this one's being dedicated to being the sign. And since what we're used to seeing, this being a 0 usually means positive to us, we'll say that if this is a 1, it's a negative number. So they call this the sign hyphen magnitude format. So the way we would represent positive 14 is exactly like this in binary, and the way we would represent negative 14 would be like this. Negative 1, 3, 0. So this would be negative 14. So really it's the same thing, only this changed to be on. Now with 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, with 8 bits, and forgetting about this negative business, what is the range of numbers we could represent? We could have represented numbers between 0 and 1, 2, 4, 8. No, this would be 0 through 50. 16, 32, 64, 128, 256. So it would be 0 to 255. Right? Can't represent negative numbers. Now, if we've dedicated 1 bit to just being the sign, we've actually lost a bunch of numbers, right? So what can we represent numbers? Now we can represent numbers between 2, 4, 8, 16, 32, 64, 128. It's now going to be negative 120, negative, so it goes, with 7 bits, you can represent numbers between 0 and 127. And if this is our negative, if this is our bit that tells us if it's positive or negative, we can go from negative 127 to positive 127. And one thing that's a little bit odd is we have 2 ways of representing the number 0. We have 0, and then we have negative 0. Right? So a 1 with all zeros after it means negative 0, which is also 0. So that's, you know, not a big amount of ways, but there's some ways there. Okay, so that's one way to represent negative numbers. Dedicate one of the bits to being positive or negative. I don't think there's any way to not dedicate a bit to it, for positive or negative. But there's another way of representing negative numbers. And this might sound a little strange at first, but it actually will help us with the subtraction problem. So if we think of the numbers as just going around in a circle. So let's say we had 0, 1, 2, 3, 4, 5, 6, 7. I'm going to use 4 bits. And you decided you wanted to do 5. So I'm going to use, in this case, I'm going to use 4 bits, but the high order bit will tell us positive or negative. If we wanted to do 5, no, let's say we wanted to do 3. 3 plus 2. Positive 3, positive 2. We wanted to add them together. I'm going from 3 and then I'm going 2 more units in this direction. So I do an adding operation. Okay, so I'd add them up. And I get 0, 1, 0, and I get to 5. If I had a way of representing, so on this side I'm going to represent the negative numbers, but I'm going to make it look like we're just going 1 more than we were before. And so if I wanted to go in the direction of, like what, for example, what number should go next to 0 so that that number plus 1 would equal 0. So like what, yeah, so for example, what number, if you added a 1 to it, should equal 0? Negative 1, right? So negative 1 plus 1 should equal 0. So negative 1, however we represented negative 1, if we added 1 more to it, it should become 0. So what binary number, if you add a 1 to it, would come up all zeros? So we want to take some binary number, x, 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 and if we add a 1 to it, we're going to get 0, 0, 0, 0. What would those x's be? Yeah, if they were all 1s. It's a strange thing to get used to, but if these were all 1s, Now we said our first bit is going to mean negative or positive, so this is actually some representation for a negative number. But what we'd like to be able to do is we'd like to make adding and subtracting synonymous when we mix in negative numbers. So if these were all ones and we added a 1 to it, what would we get? 1 plus 1 is 0. 1 plus 1 is 0. Carry the 1, which is 0. Carry the 1, which is 0. Carry the 1, which is 0. We'd actually get a carry 1, but we don't have room for it. But anyway, it's a strange idea, but if we use all ones to represent...
Wouldn't that be 3 though? Because when you do the 1, oh no, you're subtracting, aren't you?
Well, no, we're adding here.
Yeah, but, oh, okay, oh no, all right, never mind. Oh, okay, yeah, I messed up. I see where it is.
Yeah, this does take a little getting used to. It's just a strange way. Intuitively, the thing we talked about before, the sign magnitude, that would be like an intuitive way to represent negative numbers. Use the high bit, 0 means positive, 1 means negative, and everything after that is the absolute value of the number. That's kind of intuitive. But we can make the math of our electronic equipment very easy if we notice this. So if we let this represent negative 1, then if we were here and we added 1, we'd go to here. And then the same thing would be true for all other negative numbers, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. And I'll leave room for negative 8. We just want to convince ourselves there's room for it. But basically, if we use this representation, all ones, to be negative 1, how could we actually figure out what negative 1 is? We would use, this is called the 2's complement system. So what you do is you take a number, if you want to make a negative 1, you take the number, you flip all bits, and then step 2, you, the negative 1 would be like this. Flip all bits would be 1, 1, 1, 0, and then add 1. Add a 1 to it. So this would be the 2's complement way of getting the negative version of a number. So the representation for 0 would be 0, 0, 0, 0. 1 would be 0, 0, 0, 1. 0, 0, 1, 0, and so on. Negative 1 would be, like you just came up with, 1, 1, 1, 1. Negative 2 would be 1, 1, 1, 0. Then negative 3 would be negative 1, 0, 1. And what this really helps us to do is, if we ever wanted to say, what is 3 minus 5, even though those are two positive numbers, we could actually think of this as 3 plus negative 5. It's going to give the same result. So if we can convert 5 into its negative using this algorithm, then we can just run it through an adder. So, I mean, if we could come up with a way of coming up with a piece of hardware equipment that could do subtraction, that's fine. But we can actually treat negative number, we can actually treat a subtraction operation as adding the negative of a number. So, for example, if we wanted to say, what is 2 minus 3? So in decimal, 2 minus 3 would be negative 1. In our case, we would have 2, which is 0, 0, 1, 0. Negative 3, which is 1, 1, 0, 1. And if you wanted to know what this comes out to, you just add them together. So if we add them, we would get 1, 1, 1, 1. So 2 minus 3 is negative 1. So it's a system that works. It's just a different way of representing negative numbers. And this is the most commonly used one in computers. Not so much the sign magnitude one. So the IEEE kind of comes up with the standards all that computers should use. And 2's complement is the one that most computers use now. And then floating point numbers, which is this would be numbers that have a fraction part to them. So in decimal, if we wanted to represent 6.25, the decimal number 6.25, this is like saying 6 times 10 to the 0 plus 2 times 10 to the
-1?
negative 1, right, okay. And that means 1/10.
Yeah.
It doesn't mean 10, it doesn't mean negative 10, it means 1/10. And then plus 5 times 10 to the negative 2. So that would really be 6 times 1 plus 2 times 1/10. And then 5 times 1/100th. Add it all up. Okay. How could we represent this number in decimal? So one thing we might consider doing is this. How would we represent a 6? Oh, well, a positive 6 now, because we have positive and negative. So a positive 6 would be, a high order bit would have to be
0,
on.
1, 1.
So it'd be like 0, 1, let's say 110. We have, we'll just use 4 bits.
Four,
for
two.
them.
Oh, yeah, okay.
Okay. Does that seem right?
Yeah, 4 and 2.
Yeah, 4 plus 2. Then we have a decimal point, even though the decimal point doesn't really show up in computer hardware, but right now we're just representing it on the blackboard in decimal. I'm sorry, in binary. How do we represent 1/4? Well, we could think of it like, this is 0.110 point is going to be equal to 6 times 2 to the 0 plus, then we're going to put something, oh, there's no 6, what am I doing? This is going to be 1 times 2 to the 0, 1, 2, plus 1 times 2 to the 1, plus 0 times 2 to the 0, plus, keeping this pattern going, whatever shows up here is going to be what? I mean, we can fill in data here, 1
So
and 0.
it would be 0 times 2 to the -1. So
Right, so it'd be whatever we put here. Let's put this x, y, z. It'll be x times 2 to the -1 plus y times 2 to the -2 plus z, and we could go on forever, times 2 to the -3. What should x, y, and z be? Well, whatever we put here is going to be a half. Whatever we put in for x, so right after the decimal point, it's really going to be a half plus a quarter plus an eighth plus a 16th, and we could go on setting them to zeros and ones. So if we wanted to represent 25%, we could say it's not a half, and this one would actually be a quarter, right? If this was equal to 3/8, it would be 0, 1, 1. If it was equal to 1/8, it would be 0, 0, 1. And then whatever fraction it is, we just use that many more bits. So this is actually the binary representation for 6 1/4. It just takes a little getting used to, right? Okay. Now, what if we wanted to represent this in computer memory? We could have, for floating point numbers, we could divide it up into 2 parts. What do you call the part above the decimal point? The integer part, and then the decimal, the fractional part. So one way we could represent floating point numbers is the part before the decimal and the part after the decimal. It's one way we could do it. But that could get clumsy when it comes to multiplying and stuff like that. The IEEE decided, and every computer seems to follow this, is they've decided, well, we could, this is this is equal to 6 1/4, we could decide to move the decimal point in any direction. And we could say this. We could say 11001, moving the decimal point in 2 directions, and then say multiply this whole number by having an exponent of being 2. No, it's 4. Sorry. To the minus 2. Exponent to the minus 2, right? So we could take this number and then multiply it by 2 to the minus 2. So what is this number? 16, 32, 16, 40, 45. Does that sound right?
2, 6, 16. Yeah, right. It's 1, 2, 4, 8, 16.
Oh, no, 8. 16 plus 8 plus 1 is 25. 25 times 2 to the minus 2 is 1/4. 25 times 1/4, which is 6.25. So just another way of representing it. Another way, we could move this decimal point anywhere we want, right? And we could have decided to move it 2 places here. We could have said 1.1001 times 2. 1.001 times 2 to the now square. And this would be 1.5, not a 6, not a quarter, not an 8, but a 16. This would be 1.5, 625 times 4. It's another way of representing. We're just like throwing an idea, which comes to 6.25, a decimal again. So the bottom line is, we can move the decimal anywhere we want as long as we keep track of the corresponding exponent. So what they decided to do was, you're going to have a bunch of bits. They're going to move the bit to the point, I'm sorry, they're going to move the decimal to the point right after the first one, whatever that may be, and they're going to keep track of how many hops it was, so we know what the exponent is. Then they decided, well, because they wanted to save space, they decided, we know the first bit is going to be a 1, because the decimal got moved until there was right before, it moved to right before the first 1. So we know there's a 1 there, right?
Yeah.
So what they could have done was this. They could have said, we're going to represent the number like this, 11001 in the fractional part, and then in the exponent part, actually they usually represent it the other way around, the exponent first. They usually represent it as the sign, the exponent, and then the fraction. And sign. So they could have done this. They could have said 11001, and knowing that the decimal goes right here, we would need to, what am I doing? 11001 in the fractional part. And then knowing that the decimal goes here, they had to multiply it by an exponent of 2. 2 to the 2. So they would record a 2 here. This would be one way they could represent the number, right? Get the fractional part, keep track of how many decimal places you slid. And we could slide in either direction, and we just want to keep track of what it is. That's one way to do it. What they decided to do to save space was to say, well, we always know the first digit will be a 1. There's no actual dot here. We always know the first one's a 1. So why record it? We're guaranteed it's a 1. So they decided to get rid of it. They know it's going to be a 1, so why take up space recording it was their logic. But this is where it gets confusing. If you ever look at a dump of data and you go, oh, this is a floating point number, the first one is taken away. Now the other thing is, the decimals could go, the exponent could go positive or negative. So now we're starting to get into the situation where we have to have positive and negative exponents. And what they decided to do was, they came up with a number of bits to dedicate to each section. So for 32-bit numbers, which is called single precision, they decided to allow 1 bit for the sign, 8 bits for the exponent, and that leaves us with 23 bits for the fractional part. They get rid of the 1, the leading one, because they know it's a 1. And now the thing is this, do we want to play this game of positive and negative exponents? What they decided to do was, whatever number you want to record here, you subtract 127 from it. So if you want the exponent to be 2, you have to actually put in a 129 here. So they allow, because the distance, it'll be 255 will be the range, they'll let half of them go negative and half of them go positive. So you would have to put in a 129 here to mean a power of 2. 129 minus 127 is 2. So what's 129? That would be 128, which is a 1. 128, 64, 32, 16, 8, 4, 2, 1. That's 129?
Yeah, I think so.
Okay, so 129. Okay. This, and the sign is positive, which means that's a 0. This is the representation for 6 1/4. It's positive 129, which means the exponent is plus 2. And then this is the fractional part with the first one taken away.